Okay, so today we're gonna start talking about the notion of cofinality, via which we shall prove a theorem called Koenig's theorem, and that will be somewhat a generalization of Cantor's theorem. And via this notion, we shall also be able to figure out how the cardinal exponentiation works once we assume the generalized continuum hypothesis. So, what is cofinality? We first need an auxiliary definition. If you have a subset of a partially ordered set, a subset A of a partially ordered set, let's say we have this partially ordered set P less than or equal to, is called cofinal if the following happens. For all elements of this partial order, you can find, for every element of this partial order, you can find some element in A which is greater than or equal to this. Okay? So, what this says is, in a sense, this subset A should be unbounded in your partial order. What do I mean by unbounded? This means that whatever element you give me in this partial order, I should be able to exceed it by some element in A. Here's an example. As your poset, as your partially ordered set, take the set of subsets of natural numbers and let your partial order relation be the subset relation, okay? So this set, together with the subset relation, it's a partially ordered set. Take your A to be all subsets of natural numbers which contain, let's say, 0. Now this is a cofinal subset of this. Here is the reason. You give me any element in here, you give me any subset. I consider the set, which is the following. That set you gave me, union the singleton containing 0. And then this union contains 0, so that's the subset of natural numbers which contains 0, so it's in this set. And under this relation, it's greater than or equal to the subset you gave me. So this is a cofinal subset. Okay? So pictorially, the following should happen. If this is your partially ordered set, your elements are partially ordered by something. A cofinal subset is a subset, as I said, which is unbounded in here. So, let's define now the notion of cofinality of an ordinal. Definition. Any questions about this notion? The notion of cofinality, the notion of cofinal subset? No. Okay.
As long as this set A contains the smallest element, not least element.
Greatest element? Maybe there's no greatest element. Yeah, it can contain the least element.
Like it is cofinal.
No. No. Well, here is an example. Take this set. This contains the least element. It's not cofinal because you cannot find something in A which exceeds, let's say, 1. This says for every element you should be able to find something which is greater than or equal to that, not less than or equal to. Not the other way around. Anyway, let me define the cofinality of an ordinal. The cofinality of an ordinal alpha is the least ordinal cofinality of alpha such that there is a function f from cofinality alpha to alpha whose range is cofinal in alpha. So the cofinality of an ordinal is the least ordinal from which you can find a map whose image is cofinal. So pictorially we have the following. The cofinality of an ordinal alpha is an ordinal, and there is a map whose image is cofinal, okay? Now, let's make some basic observations about this. First of all, why does this exist? Let's consider the identity map from alpha to alpha. The identity map which sends every element to itself. Well, the range of this is alpha itself. The range of the identity map is the set itself. And the whole set itself is cofinal in itself, is cofinal in alpha. Now, there is some map from alpha to alpha whose image is cofinal. So there is at least one ordinal from which there exists a map whose image is cofinal, which means that there is such a least ordinal. So the cofinality always exists. And moreover, by this observation, the cofinality of an ordinal cannot exceed the ordinal itself, because worst case, I can find a map, like I have a map from alpha to alpha whose image is cofinal, which is the identity map. So let's keep this observation on board. Now, the cofinality of a successor ordinal is 1. Why is this true? Because if you have an ordinal which is a successor, then this guy has a greatest element, alpha. If you just look at the ordinal 1, which is the singleton 0, and send 0 to alpha, then this is a cofinal map. Just look at this map. 0 goes to alpha. This is a cofinal map. The image of this map, which is the singleton alpha, is cofinal in this ordinal. So I have this. Well, what else do we want to observe? Now we want to observe some examples. We want to see some examples. So cofinality of omega is omega. The reason is that if you try to write down any function from a finite ordinal to omega, its image will be finite and hence not unbounded in omega. So this is the best you can do. Cofinality of omega 1 is omega 1. And the reason for this is the following. So this is the least uncountable ordinal. Let's say that the cofinality of this guy is less than omega 1. If the cofinality of this were less than omega 1, it would be a countable ordinal. And there would be a map whose image is unbounded. But here's the problem. If you have such a map from a countable ordinal to omega 1, its image consists of countably many countable ordinals. This is a set of countable ordinals. This image consists of countably many countable ordinals. The supremum of countably many countable ordinals is countable because a countable union of countable sets is countable. Thus, if you take any map from a countable ordinal to omega 1, its image, like when you take the supremum of its image, it has to be a countable ordinal. So the image cannot be cofinal, which means that the cofinality of this guy cannot be less than itself, so it has to be itself. Let's see an example where the cofinality is smaller than the ordinal besides this one. The cofinality of aleph omega is omega. And here is the reason. Aleph omega is the following cardinal. It is the supremum of aleph 0, aleph 1, aleph 2, dot, 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 dot. It's the supremum of these guys. If you look at the map from omega to aleph omega, which sends 0 to aleph 0, 1 to aleph 1, 2 to aleph 2, and so on, you send n to aleph n, the image of this map will be cofinal because this guy is supposed to be the supremum of all these guys. Okay? So there are limit ordinals whose cofinalities are smaller than themselves. Okay? Now, let me assign a little exercise, which is not difficult to prove. Show that this ordinal is always actually a cardinal. Okay? And this is somewhat easy to prove. Take an ordinal alpha, look at its cofinality. If this were not a cardinal number, there would be a smaller ordinal with which this guy is equinumerous. But then, taking the map with this domain to alpha, whose image is cofinal, if you take that map and compose that map with the bijection between this guy and its cardinality, then you would find the map from the cardinality of this ordinal to alpha, whose image is cofinal. But that shows that, like, that gives you a contradiction if you assume that that cardinality is strictly smaller than this. Okay? So just by the definition of a cardinal number, you can show that this is actually, like, this ordinal is always actually a cardinal. So that's that. Now, I'm going to prove a small lemma. Which is going to tell us that while considering cofinalities, we can actually restrict our attentions to increasing maps instead of all maps. Let alpha be an ordinal. Then there exists a strictly increasing function f from cofinality of alpha to alpha whose range is cofinal in alpha. So what this says is basically, in the definition of cofinality, I could have replaced the word map with the word strictly increasing map. It would give me the same notion. So while considering cofinalities, I don't have to look at all maps. It suffices to look at strictly increasing maps, okay? Because from the cofinality of alpha to alpha, I can always find a strictly increasing map with cofinal image, okay? Now, how is this proved? This is proved by a recursive argument. So, case 0, this is the stupid case. This is the case where we are going to assume that alpha is a successor. This is a stupid case because in this case, alpha is successor of some theta, and if you look at the map from 1 to successor 1 to alpha, given by f of 0 equals theta, it satisfies the requirements. It satisfies blah blah then blah blah blah, and the map given by blah blah satisfies the requirements. This is a strictly increasing map with cofinal image, so that's fine. So this is the stupid case. Now the real case. Alpha is a limit ordinal. Now, here is what we're going to do. In this case, first, let's take a function from cofinality of alpha to alpha with cofinal image. So let G be a function whose image is cofinal in alpha. Consider the map F from cofinality alpha to alpha defined by transfinite recursion as follows. So I'm going to define this map F, which is supposed to be strictly increasing, by transfinite recursion. So I have to tell you what to do at an ordinal by looking at what we have done on the previous ordinals. So let's look at this. The value of f at an ordinal theta is given as follows. You first look at the value of g at theta, and you look at all the values you've computed so far, and you add 1 to these, and then you take the supremum, and then you take the maximum of these guys. Let me erase this board as you process this line. So this definition makes sense for all theta less than cofinality of f. Okay, so I'm defining f like this. Now I claim that f satisfies the requirements. Why? what am I doing? Let's understand this pictorially. So I have this map from cofinality of alpha to alpha whose image is cofinal. Okay? So this is my G. What I'm doing at any ordinal is the following. At ordinal theta, I first look at all the previous values I've obtained. I look at all the previous values. I add 1 to these guys. So now I'm exceeding all of the, well, I'm not exceeding anything. I'm adding 1 to all of these guys and I'm taking the supremum. So this is the supremum of these guys. And I am taking the maximum of this ordinal and the image of G at theta. Whichever is the maximum, I take that value. Now what does this guarantee? First of all, this guarantees that, like this definition guarantees that the image of F is cofinal. Why? Because, let's see, it's easily seen that because F satisfies this. At any point, F is defined to be the maximum of these guys, and this is like G of theta. So at any theta value, F cannot be less than G. And a consequence of this is that the range of F is cofinal. Why? Because you can, given an element of alpha, you can exceed that element with an element in the range of G, but you can't exceed any element in the range of G by an element in the range of F. So range of F is unbounded in alpha. Think of it like this, like range of G is cofinal in alpha, and range of F, you can exceed any element of range of G. Okay? So this has to be cofinal. Range of F has to be cofinal as well. So that's that. And F is strictly increasing. Why? That should be also easy to see. I'm adding 1 to all these previous values and taking the supremum. This guarantees that taking the supremum of f of psi plus 1 guarantees that f is strictly increasing. Okay? So this f works. Now, questions?
Here, case 0, case 1. Do these numbers mean something? Like case 0?
No.
We could make it case 1, case 2 as well, right?
Well, if you want, I can make this case, this smiley in case that smiley. Indeed, let me leave it like this. Okay. Now, another exercise. Show that for a limit ordinal alpha, we have that cofinality of alpha is the same as cofinality of aleph alpha. This is not difficult to prove. Let me tell you the easy direction. Like, you're supposed to prove that two ordinals are the same. So it suffices to show that one of them is less than equal to the other and the other is less than equal to this one. So let me tell you one direction. Take the map from cofinality of alpha to alpha, which is strictly increasing and whose image is cofinal. Take the map from alpha to aleph alpha, which sends any theta to aleph theta. Compose these maps. If you compose these maps, you're going to get a map from cofinality of alpha to aleph alpha, whose range is cofinal. And that will show that the cofinality of aleph alpha cannot exceed cofinality of alpha. Okay? And then for the other direction, you have to do something else, which is not that difficult. I'm going to let you think about that. So that's that. And now I want to make some definitions so that I can actually state Koenig's theorem. Let's say that I have an index set of cardinals. Now, what I'm going to do is, I know how to add two cardinals. I know how to multiply two cardinals. I'm going to tell you how to add and multiply a lot of cardinals together. You have an index set of cardinals. We define its sum and product to be the cardinalities of blah blah and blah blah respectively. So let me make the definition. Okay, I have an index system, index system of cardinals. I want the sum to be the cardinality of the disjoint union of these guys. So how do I do that? I'm going to take the ith cardinal here, and I'm going to take the Cartesian product of that with the singleton I, and I'm going to take the union of this set. This is the disjoint union of this system of cardinals. What I'm doing is I'm creating a copy of each kappa I, and I'm taking the union. When I take this Cartesian product, these are now become disjoint, these sets. I'm taking their union. Okay, so this is the disjoint union of these guys. And the cardinality of this is defined to be the sum of this index system of cardinals. Okay? So the cardinality of this is the sum of these cardinals. Well, I'm defining the sum of these cardinals like that. And the product of this index system of cardinals is the cardinality of this product. We know how to define product of an index system of sets, right? Take that product, the cardinality of that is defined to be the product of this index system of cardinals. Now I'm going to abuse the notation and use this to denote both the product, like the generalized Cartesian product of this index system of sets and the cardinality of this set, okay? So I'm creating a bit ambiguity here, but it's not going to create any problem, don't worry. So when I write this, I may mean one of the following two things. The generalized Cartesian product of this index system of sets or the cardinality of that. Okay? Now, that's that. So, given an index system of cardinals, their sum is the cardinality of their disjoint union, their product is the cardinality of their Cartesian product. Okay? And if you remember the definition of cardinal addition and multiplication of two cardinals, you'll see that this basically generalizes those definitions. Now let me state Koenig's theorem. There are multiple important guys in mathematics with surname Koenig. I think they're related. This is the one whose first name is Julius, I guess. There's also Koenig, the combinatorialist, the graph theorist, I guess. Well, maybe he's not a graph theorist, but he has some theorems in graph theory, so that's why I always assume that he's a graph theorist. Anyway. Here is Koenig's theorem. Let's say that you have two indexed system of cardinals. B indexed systems of cardinals with lambda I strictly less than kappa I for all I and I. So you have this possibly transfinite list of cardinals, and you have another list, and each element in here is strictly less than the corresponding element in here in this list. Okay? Then sum of these guys is strictly less than the product of these guys. Okay? Now, I have how many minutes? 10 minutes. So this is important. I want to do I don't want to try to squeeze the whole proof into 10 minutes. So what I'm going to do is I'm going to assume this and prove its corollaries this lecture. Next lecture I'm going to prove Koenig's theorem, okay? For now we shall not prove this at the moment, but will obtain some of its corollaries. So this will be proven on Thursday, but let me derive some consequences of Koenig's theorem. The proof is going to be basically a diagonalization argument, not that there is anything conceptually really difficult with it. It's not that difficult, but yeah, I want to spend some time on it, so I don't want to do it today. Now, the first corollary of this is that for any infinite cardinal, kappa kappa is strictly less than kappa to the power cofinality of kappa. Remember, Cantor's theorem told us that, okay, remember 2 to the power kappa is equal to kappa to the power kappa, and Cantor's theorem told us that this is strictly greater than kappa. So kappa is strictly less than kappa to the power kappa. This is somewhat better. It says that it suffices to raise kappa to the power cofinality of kappa in order to exceed kappa. Okay, well, this may or may not be kappa, but the worst case, this is kappa. This is like cofinality of kappa, remember, is less than or equal to kappa. So this is why this is a generalization of Cantor's theorem, in a sense. Okay, so here's the proof. Let kappa be an infinite cardinal, and f from kappa, cofinality of kappa to kappa, be a strictly increasing map with cofinal image. Well, I can find such a map because of the lemma we proved, okay? Then, now it's going to be, the essence of this proof is going to be simply one line. Then, now, f of xi is strictly less than kappa for any xi in the domain. This is simply by definition, okay? The codomain of this function is kappa, so f of something is always strictly less than kappa. Then, since this happens by Koenig's theorem, we have the following. Now, the image of f is cofinal in kappa, which means that if I take the supremum of the image, I'm going to get kappa. Okay? This is kappa, this is cofinality of kappa. I have a cofinal map. Cofinal map simply means that its image is cofinal, okay? So I have this cofinal map from cofinality of kappa to kappa. If you take the supremum of the image, if you take the supremum of all these ordinals, you're going to get kappa. And this is less than or equal to this sum. Why? How is this defined? This is, okay, my index set is cofinality of kappa. I have an index system of cardinals. I take their sum. How do we define this? This is the cardinality of the disjoint union of these. Okay, I take the disjoint union of these guys, I take its cardinality, and that's the sum. What is the supremum? This is literally the union of these guys. So over here I have union of these f of xi's. Over here I have the disjoint union of f of xi's. Clearly, the cardinality of this is, the cardinality of the disjoint union cannot be smaller than the cardinality of the union. So I have that. Now by Koenig's theorem, this is each f psi is strictly less than kappa, and I'm adding f psi's here. So this cardinal is strictly less than the product of cofinality of kappa many kappas, but this is like, how do we define this product? This is the cardinality of the generalized Cartesian product of this index system of sets, where each set is kappa and I have cofinality of kappa, many of them. This is literally, that generalized Cartesian product is literally the set of functions from cofinality of kappa to kappa. And by definition, this is the cardinality of this. Well, guess what? This is how we define cardinal exponentiation. Okay? And that's that. Now, one more corollary. And then we're going to stop. By the way, sometimes people call this theorem Koenig's theorem, okay? Not the version I stated. For any infinite cardinal kappa, we have the following. Cofinality of 2 to the power kappa is strictly greater than kappa. And again, the proof is basically 2 lines. So let kappa be an infinite cardinal. It follows from the previous corollary, from that corollary, that Now, let me take the kappa in the previous corollary to be 2 to the power kappa. So this is my cardinal, 2 to the power kappa. I'm raising this cardinal to its cofinality. Like this is of the form lambda to the power cofinality of lambda. By the previous corollary, well, okay, let me try to compute this. Like by properties of cardinal exponentiation, this is 2 to the power kappa times cofinality of 2 to the power kappa. And we proved that the product of 2 infinite cardinals is what? What's the product of 2 infinite cardinals?
Maximum.
Their maximum, good. So this is supposed to exceed this cardinal 2 to the power kappa. Theta to the power cofinality of theta exceeds theta. And so, well, let's look at this final inequality. When I raise 2 to the power maximum of these guys, I apparently exceed 2 to the power kappa, which means that the maximum of these guys is not supposed to be kappa, because if this maximum were kappa, then 2 to the kappa would be strictly greater than itself, which is a contradiction. So this guy has to be the bigger one, and it has to exceed kappa. And so cofinality of 2 to the power kappa is strictly greater than kappa. Okay? Now, in particular, let me plug in Aleph 0 for kappa. We have cardinality of 2 to the Aleph naught, sorry, we have a cofinality of 2 to the Aleph naught to be greater than Aleph 0. So cofinality of cardinality of real numbers is uncountable, okay? Now, remember continuum hypothesis, which we talked about last time. The continuum hypothesis states that this cardinal to L flat is L1. And I told you that like this cannot be proven or disproven from our axioms. It's independent. And I told you that it can be anything, right? Well, it can't be really anything. It can be anything up to this theorem. If you take any cardinal whose cofinality is bigger than L0, it is consistent that continuum, the cardinality of real numbers, is that cardinal. So, for example, what's the cofinality of this? The cofinality of this is omega 1. Okay? So it's greater than L if not, which means that it is consistent that continuum equals this. This can happen. It is consistent. So continuum can be any cardinal as long as you don't violate Koenig's theorem. You can't make this. This cannot happen. Because what's the cofinality of LF omega? It's omega, so it's LF naught. But I know from this corollary of Koenig's theorem that the cofinality of this should be greater than omega. So this cannot happen, but this can happen. And this can happen as well. The point is, with this technique called forcing, you can show that as long as you don't violate this inequality, you can make continuum anything. It is consistent that continuum has any value as long as the cofinality of that value is uncountable, okay? Now that's that. And now I'm going to stop. Next lecture, we're going to prove Koenig's theorem. It's not going to take a lot. And then I'm going to talk about singular and regular cardinals. And we're going to prove, we're going to find the value of a cardinal exponentiation assuming GCH using the notion of cofinality. And after that, there's a little section about von Neumann hierarchy, the cumulative hierarchy, which somehow gives you a picture of sets. Okay, it's like a stratification. It's like a stratification of the universe of sets. It gives you a picture of the universe of sets, and I'll try to finish that, and then we will conclude the class. Okay, when we do that. So I'll see you on Thursday.